Assessing Ecosystem Health with Copernicus Marine Data. Today is a practical session of our workshop. Yesterday we had an introductory section. We hope you were able to learn a bit more about the Copernicus Marine Service. We shared some interesting use cases, and we spoke also about our extensive catalog of products. Today is the time to put your hands on the data. My name is Andreia Carvalho. I'm a training officer at Mercator Ocean International, and I'll be your host for today. So before we start, I'll give you some guidelines for today's session. You are, at the moment, you're on Zoom. This is the platform we are using for the workshop. We also have a chat on Zoom where we can do small talk. But for any of your questions related to the workshop, any questions you would like to pose to our speakers today, we will be using Slido. You can see it on the screen. And we will also share our link to a Slido platform where you can post your questions, and we will address them at the end of each presentation. So here's the code you can also insert in Slido session. It's specific for today's session. Another something else I wanted to show it to you is the Padlet. If you were in yesterday's session, you've seen that this is a platform that we use for all the resources related to the workshop. There you will find the participant manual with very useful links on resources, but also on to, for example, register yourself on the Copernicus Marine Service, how to access the data, how to access the Jupyter Hub, etc. Also, all the replays will be posted in the Padlet. So if you're not able to follow today's session, you will be able to see it later on. Also, the replays will be posted on our YouTube channel, Copernicus Marine Service, a YouTube channel. So you will be able to follow that. Yesterday's presentations and today's presentations will also be posted on the Padlet. So it's basically your platform for all the resources of this workshop. Just some more general or more, in this case, more specific guidelines for today's practical session. We will have 2 tutorials, and the first one will be on a Jupyter Notebook tutorial. Some useful tip would be if you want to follow along, try to do it by yourself. You can start by registering yourself on the Copernicus Marine Service so that you are able to access the Jupyter Hub. We will explain you a little bit more in a minute, but this could be something that will make you gain some time in a minute. And now I will present you the speakers for today's session. We will have Alvaro de Pascual Collar and Stefania Ciliberti, who will show us very interesting tutorials. They are representing Nologin, and they have developed these super interesting tutorials. We hope you can join in. We advise you not to just follow it, to see it if you are a beginner. If you are a bit more advanced on both Jupyter and Jupyter Notebooks and QGIS, you can try to actually perform the tutorials as we go. But the idea here is just to really show you how to handle the Copernicus Marine data, how to extract it, how to display it, and if you have any questions along the way, our experts are here to help you. I will introduce you to Alvaro de Pascual Collar. Whenever you want, the floor is yours. We'll start with the first tutorial.
Hi, good morning to everyone. Well, today we have two tutorials in Jupyter Hub. The first one is a basic tutorial on how to have some use of the data of Copernicus services. We have focused this visualization in the theme of assessing ecosystem health, but at the end is quite standard tutorial about visualization of data that can be applied to any data in Copernicus services. And after that, we want to we are going to do a tutorial on explaining how to compute marine heat waves using Copernicus services data. To go to the Jupyter Hub, here in the Padlet you have this link, so you just have to follow this link. And well, as Andrea said, you will need an account in the Copernicus services, and you can enter in this using your username and your password. Okay, and you will find this. You can see that in this screen you have split it into two areas. There are the two areas. In the left panel you have a file browser that usually starts here in your home directory. Here I have some files. Any user probably will have different files here, but everyone should have this folder, shared notebooks. This folder is quite important now. And in the left panel, in the right panel, sorry, we have this. This is a workspace where we can see launchers for to launch notebooks, which is the main tool we are going to use today. We will see later how it works, and there is also interesting this icon, which is a terminal. We can click here, and we enter into a Linux terminal, so we can work here like in a Linux machine, right? So as in every Linux machine, we can put a double, so we can see the files that are in our home directory, right? They are the same files that appear here in the file browser. Well, it's interesting to know that what have to do to start working. The first thing we have to do is to get the course and to copy the course into our home directory. So as I said before, there is here a folder, shared notebooks. You can follow this folder, and you will see that there is a list of courses that you can download any course, and you can follow any course here. Today's course is this one, the Training Assessing Ecosystem Health 2023. So, but you can enter in this course and you can see whatever the things that are associated to this course. But it's important to know that you cannot run the courses in this directory, because shared notebooks is a directory, it's just an storage directory, and you don't have permissions to write in this directory, so you cannot make changes to it. So the first we have to do is to copy this directory to our home directory, and then we can start to work in our own copy of the course, right? So, well, to do this, we are going to use a Linux command. Probably people familiar with Linux will know. So in Linux, to copy a directory is we use this command copy -r, because it is a directory and we want to do it recursively. And here we need the path of the directory we want to copy. So to find this directory, we can go over here, and with right click, there is here an option that copy path, and with Ctrl+V, we can copy the path of the directory we want to copy. And the last argument in this command is the location where we want to copy the directory. So in Linux we use dot to refer to the directory where we are already are. Well, we hit enter, and this can take some time, maybe a few seconds or maybe a minute. During this time, we can go back to our home directory here, and you will see that during the copy, you are starting to have this directory, which is the directory you are copying. Oh, I think this is taking a little bit more time than usual, maybe because there are lots of users right now. Oh, okay. It has finished, and while when the copy is finished, you can close this window because we have our directory copied here in our home directory. And well, we can start to work properly in what we want to do. We can close this window right now, and you will see that in the directory of the training course, you will find two different Jupyter Notebooks files. The first and the second one. The first one is the basic tutorial. We are going to start with this tutorial right now. So you can open this tutorial and you will see that it opens in a new window here. I don't know if you are familiar with this kind of tutorials or with this kind of documents. A Jupyter Notebook document is a document that mixes some documentation, like you can see here. For example, we have a lot of text explaining things, and it also mixes cells with code. To run these cells with code, as you can see here, you can click on the cell and click the run button here, for example, and you will see here the process of running. When we click in run, there is here an asterisk, and when it finishes the running, appears a number. So while there is an asterisk, the cell is running, and when it finishes, there is here the ID of the command you sent, right? Well, we'll see about this later, about this code. I just wanted to introduce this tutorial, talking about, well, what means assessing ecosystem health. And most important is what can provide Copernicus services to help in assessing ecosystem health, right? Well, as probably most of you will know, there is many models that allows to evaluate the health of an ecosystem. And these models always work with a lot of variables because the health of an ecosystem is sometimes threatened not only for biological variables, they are also threatened by physical variables and very usually for social variables. So the models, the models usually, the current models used to evaluate the health of an ecosystem uses five, for example, in this model, 5 pressure state impact and response model, use different groups of variables to evaluate the state of a system. As you can see in the layers of the state, and well, the Copernicus services can provide not data, not in every layer, but yeah, it can provide lots of data, especially in the layers of the state, to define the state of the ecosystem and also to evaluate the impact of the changes we made, right? To evaluate the state of the ecosystem, we can provide lots of variables, like variables about acidification, nutrients, turbidity, tidal range, because sometimes it is also important for the health of an ecosystem, temperature and salinity, because they can also have a role in the health of an ecosystem. There is also variables about dissolved organic carbon, pH, etc. Also distance about of ice to the coast, etc. Right? Well, in this case, we are going to download data of probably a very important model. In this case, we are going to download data from the global biological geochemical model. And we are going to see what this model can provide, what variables can provide, and we are going to see some visualization of the variables. And to do that, well, the people which is familiar with Python code probably will know that in Python, first thing we usually do is to launch the libraries we are going to use in our code, right? So this is the first setup of our system. Here you can see we are going to use different Python libraries. For example, these warnings is not an important, it's just to avoid warnings. But the important ones are this NumPy and XArray, which are libraries for numerical computation. In the case of NumPy, and XArray is very useful in our case to open netcdf data files. You will see that in Copernicus, every data file is stored in netcdf format. So this library is very useful. And we also use different functions from matplotlib, which is a Python library, very famous library used to make plots, scientific plots. And also we are going to use Cartopy, which is a library that is oriented to help making plots, but not flat plots, to project plots over maps. So you can include coastlines, you can shade the terrain, or you can use different projections like Mercator projection or cylindrical, etc., conical, etc. Right? But we are going to use Cartopy. Well, and the first we have to do to start working, obviously, is to go to the Copernicus services and to go to the Copernicus Marine Data Store and download some data, right? Because we need data to work. Well, in this case, here in this table, I introduce the information you need to download your own data. First of all, I will say that in this case, we have a directory here, data, where it is included every data it's needed for tutorial. So you don't need to do this step. Yeah, I think it's very interesting because it's important step that you will have to follow if you want to do your own study, right? So, for example, here I give you the information you need for this first tutorial. You will need to download the data from this product that you probably know. The Copernicus product. Every Copernicus product has an ID code. This is the code we are going to use. You can follow this link. And you will go to the Copernicus Data Store webpage where you can see the product, where you can see the product. You will see that the product has its own product ID. And when you go to the downloading page, you will see that every product also has a list of data sets. These data sets are usually related with the frequency of the data you are downloading. For example, in this case, in the case of the data of the global model, biogeochemical, there are two data sets. One of them is the daily data, and the other one is monthly data. In this case, we are going to use this monthly data. And in this web page, you can download whatever you need. For example, you want to download monthly data for excluding some variables like this. And also you can select a window to download a specific region in the world, and you can select the specific dates and a range of depths, right? Then you can click here to download, but it is very interesting also this button, add a request. We will see later what this means, and you will find this instruction, which is quite astonishing, but it's very useful. We will see later. Well, so with this information, you can go to the web page, to the data store, and download the data you need. But as I said before, we already have the data. But you can also use the Motu client. The Motu client is a system that allows you to download data, not using the web page, but using an instruction, a very long instruction, like you can see here. It is really, really long. But in this instruction, you are requesting through Motu client some request of data, some data. So in these instructions, you have to define the service ID, as I said before, the ID of the product which you want to download. You need also the data set. You need also information of the range of dates you want to download. And also, for example, information of depth you want to download, variables. If you want some different variables, you can make a list like this, for example. And well, at the end, there is also two parameters, the output dir, and also the output name of the file. And these ones are very important because you have to include here your username and your password, obviously, because you are accessing the Copernicus services data store. So you need to access with your user and your password. So you have to change here your user or your password. Well, I don't spend more time on this, but I just want to show you how works this. For example, downloading this here, we are downloading two different files. For example, this one, Python, and this one, and there is another instruction because later we will need a different file. So I just want to show you how can it work, but since I don't want to share my username and my password, my Copernicus password, I am going to use this little trick just to hide my user and my password. And well, you can run this cell, and probably you will see that you sent a request to the Copernicus services, and this can take maybe 1 minute or two in downloading the data. But well, you have this is because when you are doing a request to the services, you are requesting a specific period of time, a specific window of data, specific variables, etc., etc. So the system has to find in a huge database, in the huge database of Copernicus services, it has to find the data you need, and it has to create the file, format the file. Well, sometimes it doesn't take too much time. Right now, maybe, I don't know. Well, we can let it be for a few seconds. Maybe we will, okay. It starts when you, in this period, the system is preparing the file you are requesting. Now, once the system finds the data, you start with the downloading, and you can see it downloads pretty well. Just a hint. What do you have to do to be able to use the Motu client in your system? I included here a link to the help page of Copernicus, to one help page of Copernicus that I think it's very useful and very simple and go straight on. You just follow these instructions and you will be able to use the remote client in your system, so you can use this kind of instructions in your system, and you can. This is very useful when you have to download data. Download data recursively, because once you have this instruction, that, as I said before, this instruction can be found here, because you have to select what you need and you get the instruction here. And once you have this instruction, you can start to play with it, changing, for example, the dates you want. So you can download different dates, different files with different dates, and you can start to play with the variables you download or the depths, etc. So you can split the downloading data of data, right? Well, so we already have all data, but what can we do with this data? Well, first of all, we have to open this data and get it accessible for the system. So in Python, we use to do that. We use, as I said before, the XRI library. It's a very useful library because any data downloaded through from Copernicus services is stored in a PDF format. Probably for people who is not familiar with this data format, I will say that this format has three kind of objects inside a file. There you will find three types of objects: the variables, the dimensions, and the attributes. Let's say that variables are the arrays of the data itself. And these are the arrays you will need for this is the multi-dimensional arrays of your data. And also you will find the dimensions, which are some special one-dimensional variables that define the dimension of the different variables, and also attributes that are actually labels that maybe can provide information, but they are not very useful. Well, we can run this cell to open a data set. Here you have a cell where we use the XRI library using the function open dataset, and we include after the as a parameter for the function the file name of the path and the file name of the file we want to open. And you can see that this will create a new variable, a new object that we have called DS, and here we are printing info for DS. So if we run this cell, we get this, which are when we print this, when we write this, we get a small report of the data stored in DS, and we get this. You can see here we have 4 dimensions, as I said before. The dimensions in this file are depth, latitude, longitude, and time. You can see also the length of every dimension. Depth only has 1 layer. Latitude, we have 600, more than 600 latitudes, values of latitude, more than 1,400 values of longitude, because we have downloaded the data for the world. And we also have 13 time steps. You can see here some more information about the variables. Here you can click and get some reports, some information, and you can get the attributes of every variable. For example, in the dimension latitude, we have these labels that you can see. There is information like units and log names, etc. And well, we have the information of latitudes, longitudes, dimensions, and here we have all the variables we have downloaded. Here, I think it's the most interesting right now, because here we have a quite wide spectrum of different variables. For example, we have here information of partial pressure of CO2. For example, O2, oxygen, concentration of oxygen, chlorophyll. This is nitrate, phosphate, phytoplankton, total phytoplankton, silicium, pH. This is excuse me. This is total alkalinity, net primary production, dissolved organic carbon, and iron, concentration of iron. You can see there is information of many nutrients like phosphate, nitrate, and iron, oxygen. So these are the kind of variables that Copernicus services can provide most of time for assessing ecosystem health. Here we are focused in geochemical variables, but obviously the Copernicus services also can provide physical variables like temperature, salinity, significant wave height, etc. Right? Well, we have our data. You can see here we are working with quite big array, 4-dimensional array. Well, since this is dimension 1, there is just 3-dimensional array, right? Actually, but we are working with an array of lots of values. Well, what can we do to access this data, right? The interesting thing is what we have the data here. The data file is open. So what are we gonna do? What can we do with this? Well, for example, I want to explain how to plot a simple map of one of these variables. In this case, I will plot, for example, here I am defining some simple variables, character that we will need to work. For example, we want to plot, for example, CHL, which is chlorophyll. This is the name that appears here in the report. So if we want to plot chlorophyll, we refer to chlorophyll like CHL variable. We are going to plot a map of one specific date, because to plot a map, we will need an array of 2-dimensional array, obviously, because to plot a map, you need 2 dimensions, latitude and longitude. So at the end, you need to select the data you want to plot, selecting what depth, which is only 1, and the specific time you need, right? So, for example, for this example, you can change this, and you can go and click modify this and see the results. I selected this date, February 2023. This is interesting to have it also. The name of the dimension latitude and the name of the dimension longitude. This information can be found here in the report we had when plotted GIS, right? Well, with this, we are using a function from XArray, which is cell function, very important function about XArray, that will select the specific data we are asking here. For example, you can see here we are referring to DS with the name of the variable. So with this, we are selecting the data of DS of this variable, which in this case is chlorophyll. And from this data, we are going to select in the dimension time the specific date we want to plot, right? We are using the method nearest. That means that we are looking for the nearest date to this request. Well, this is just to remove any dimension with size equals to 1. Well, this is a technical thing that maybe doesn't matter right now. If we run this cell, we will get this. You can see here with this command. With this command, we are getting a new variable that is data to map, and we print data to map, and we get a variable with an array of two dimensions, latitude and longitude. Only one, these two dimensions. And well, I think there is not much to explain about this array, just that it has two dimensions, and we can go directly to plot this variable. How to do that? We have included this cell. Here you can see that we have defined a function that we have called plot map, and after defining the function, we use the function plot map. If you don't mind, I will run this function. You will see that this function right now takes quite a long time to run it, so I will do it, and later we'll continue explaining this. The function is running, and you can see it takes quite a long time. Later we will talk about this. Explaining a little bit about the function we are using. This function defined. We have wanted to do this in this way because I think it's interesting for you. You can cut this function from here and put it in your own code, and you can still use this function for your own code, and it should work. So the using of functions inside Python I think is very interesting because you can make much more modular the code, and since you have this function here, you can cut this function, include it into your code, and it should work like it works here. Well, the function, you will see that there is 4 chapters. In the first thing we do in the function is to create a figure and an axis inside the figure. These are technical commands inside Python. And since we have defined the axis as with a graphical projection, we can start to work with, we can define the map features, like, for example, we want to draw the coastlines, we want to draw the latitude and longitude lines. The function has finished, right? We get this map. We will go over the map. Or some instructions, like if we want to mask the land, for example, etc. And here it is the instruction, the command to make the specific plot. To make the plot, we use this function from this is matplotlib. This is a P-color map, P-color plot, which means make, as I said, color, and we have to give it information of latitude, longitude, latitudes, and data. The specific data, would be the set axis, and the color map we want to use. This is commented right now. We will go over there later. And here we include some editing commands. For example, the title of the title of the plot, and the color bar. We want to include the color bar, etc. The ticks, the size of the ticks, and the labels, etc. And when we run this, well, as you can see here, we have a map of the chlorophyll concentration all over the world. Well, this is quite much blue, right? This is there is 2 things here. The map is quite much blue, and also the functions has took long time to run. Let's go over the second point. Why this took so much time? Well, it is because we are working with a very big array, so the system gets difficult on finding the memory, etc., to plot this map with so much information. How can we improve this? Well, so for example, as you can see here in this cell, I include 2 options. 2 options that are not mandatory, but can we apply it? Option 1 allows you to subset a range of latitudes and longitudes in your map, so you can make a map in a specific location. For example, I don't know, in Japan or in Canada, whatever place over the world. I will let this option if you want to play with it. I think it's interesting, so you can see how it works. And we also have this option that I'm going to uncomment, that as you can see, we define a variable which is skip, and we use again over the variable data to map, we use again the cell function to cell a slice of latitudes and a slice of longitudes. But actually we are not slicing the variables, we are using the slide procedure to skip some data. So with this, since these data are defined, the variable skip is defined as 4, we are selecting every fourth data in the array, right? So as you can please look at this, the latitudes are 600 and 1400. If we run this again, we obtain a new array. Data to map is a new array, but it has a lot less values, right? It's a smaller array. So if we go over the plotting cell, this takes a few seconds, but as you can see, the result goes a little bit clearly faster. It's clearly faster. Obviously, we have lost resolution in our map, but sometimes it's interesting because you don't need so much resolution for a map of this size. So you can find a compromise between the fast of the code and also the resolution you use and the size of your maps. And if you want to plot a very huge map with lots of information, it will take time, obviously. Well, we have solved one of the problems we found, which is the performance problem. But this map is still has a lot of blue. It's not very contrasted. So, well, what can we do here? We are using, you can see, we are using a linear color scale. And this is a little trick, very used, very normal. It is using logarithmic normalization. This is the use of a logarithmic color scale. It's very common to use this. So we can comment this line. And with this, we are defining that in our diagram, we want to use a logarithmic normalization. So our color scale will be a logarithmic color scale. We can run this right now. And you will see that, well, it is a lot more contrasted, right? So this kind of normalization is very, very, very common when you use biogeochemical variables. There are lots of variables that can be improved, the visualization using, as you can see here, we have a logarithmic color scale. Well, jumping to the next, just to I would like to encourage you to try to do these exercises and explore everything. If you want to plot other variables like O2 of phytoplankton, I think it's very interesting to play with this and see what can be done, or even you can also try to unlock this option and see what happens and play with it and try to plot a map of a specific region you're interested in. And well, we are now finishing the tutorial. The last step, it would be, well, we want this is very interesting. We have a world map of chlorophyll, but what about if we want to follow the time series of chlorophyll in a specific point? Well, we include this chapter here in the tutorial, where we are going to plot some time series of in this case, the variable we are going to plot is O2. I've selected this point in the world. And as before, we are subsetting the nearest grid point. So we are going to use, as before, the data set, the variable in the data set, and we are going to select this variable, the latitudes near to that, and the longitudes near to long, using the method nearest, right? This will display the data selected. Well, this is only to show a map little bit. This is just to show a map of the location we have selected. And well, we can go over this cell that, as you can see, is a lot easier because it only creates a time series. And also we are using the function plot map, the function we defined before, to make a small map of the region we have selected. For example, in this example, we are plotting the time series of oxygen in this location near in the sea, Japan Sea. And well, this is what the result, right? We get this is the time series of the system of the oxygen in this location. Well, this is just a first view of or it's just a first approach of the things you can, the kind of plots you can do with this kind of data. Obviously, from here there is a wide spectrum of things you can do, because this is just a visualization, but from here in advance you can start to make a computation over the data. So you get the data, you can do any calculus or any statistics you want, and after that you can visualize your results. So, well, this is the finishing of this tutorial. There is a final exercise. I think it's quite difficult, so take it easy. Just try the exercise, and it will be just afford this as the constructive way. So just play with it, and I think it's more interesting.
Thank you, Alvaro. Thank you for this introduction to the Jupyter Notebook. So everyone, we've seen your comments. I know it is not easy to follow along. The idea is for you to just integrate these instructions, and for those of you who were not able to register for the Copernicus Marine Service or access the Jupyter Hub, you will be able to access these materials once you have access to the hub. They will still be there, and the Padlet will always be accessible, so you will be able also to access the resources on the Padlet. The idea was to give you an idea how this works. You have all the direct instructions of Alvaro, and now we have seen you've posted some questions, so we have some questions for Alvaro. Maybe if you stop sharing your screen, we can share the questions right here. And we hope we can answer some of your questions. Let's start with the first question. Some of these questions are a bit broad. Maybe they are not specifically about this introduction, your tutorial. So the first one, do you have a tutorial about how to access the data using R?
Well, I think there is few tutorials, one or two in the.
Yes, not so many. That's true.
But we are working in a series of tutorials that will become in this autumn about how to. It will be surely quite basic tutorials about how to access the data, download the data. The part of downloading is almost the same than here in Python, but about to visualize the data and etc. and access the data will be done just now in autumn.
Yes, they will shortly be available as well. The next question, what is the CPU and the RAM limit that a user can consume in the Jupyter Hub? I think they mean the Jupyter Hub.
Well, in this case, in this system, there is limitations, but actually I don't recall it.
Yeah.
It
But
depends
it's
a lot in the system
yeah.
they're using. In this case, as you can see, there is not access to many resources because this is just a training machine. So there is not. We don't want to use this machine as a machine where the people makes calculations and etc. It's just a machine for training. So as you can see, when you use big arrays, the system gets slower.
Exactly, it's just a platform where we can make these notebooks available to you. But then, as Alvaro explained in the beginning, you have to run it in your own environment, Jupyter environment.
Yeah, it would be that idea, or I think, not sure, but I think the Wikio services are oriented to that.
Yes,
If
that is true.
If you want
can
to make
use
calculations in the cloud, I think the Wikio services are the object, your object.
You do have that possibility, exactly. Although Wikio is not totally free of charge, there's a component that it is paid, but it is true. That could be an option. I can share the link here for more information as well. And maybe another question. If there's a limit to download, how can we download all the data we need if it is bigger than the limit? Well, is there a limit for the download?
Well, I think, yeah, the answer is yes, there is a limit. I think it can be about 2 gigabytes in a file or something like that. It's not very big file, but the solution for this is using, in my opinion, is using MotoClient, because when you use MotoClient, you can split the files you want, and you, for example, if you need a very big data file, you can split a file, for example, with different datas, downloading just 1 month of data, splitting in months or splitting in geographical windows. And well, there is also an option in XRI that we haven't used it here in this tutorial, but if you shared in previous tutorials of previous courses, you can see there is an option in XRI where you can open different files and you can access a pool of files just using one object. So the system concatenates every file, so you can work it with as it would be just one file. The problem in that case is obviously it takes a lot of memory and the computations can be slowed.
Okay, so MotoClient might be the best option, right?
Yeah.
Like
I think it's the best. Or if you don't want to use MotoClient, you can split the files you need and download using the web page. But the thing is that if you use Python and XRI, you have the option of open a pool of files as it would be just one, right? So the system solves everything and it is transparent for you. You can go through the one object to all data of a pool of files.
And just to give you more details on this, if you have a specific question on an error or on the data access, you can always contact the help center, the user support for the Copernicus Marine Service. They can help you with this if it is something more specific. now there's a very specific question on an error a participant got. I don't know if you can help with this one. When I run open input data file, I've received an error, name XR is not defined. What can I do?
Well, it's difficult to
It's
say
a bit hard, yeah.
yes, in the file, but it seems that probably the user hasn't run the first cell of the code. Maybe I went fast over the cell. This is the first cell in the setup. It's the title of the cell is requested libraries. If the system cannot see the XR library, it is because the XR is not imported.
Defined.
Yeah. So probably the thing is just rerun the first cell. Just be sure that you have run the cell and without any errors.
Okay. So this one seems a bit more general. I'm wondering if your data can be used without having to validate it afterwards. I think the person Victor means Copernicus Marine Service data, or have there already been validated the validation studies of this data?
Well, maybe this depends a bit in the kind of the study you are doing. But well, the Copernicus data, they are validated. Every product has. I haven't talked about that because I didn't knew it was said yesterday that every product has his own product user manual and QID, the quality information document. And actually, the QID, the quality information document, is the document where the product is validated, and all the information we have about the validation of the product is stored. And well, before doing a specific study, a study of a specific region or something like that, when you decide to use a specific product of Copernicus, it's very recommendable to have a look to the product user manual, because it's interesting. It's the definition of the product, and you will know how the product has been produced. And also, it's very interesting to have a look to, or more than have a look, to study the quality information document, because there it is stored all the information we have about the validation. And well, it depends a lot. Depends maybe about if you are focusing in a very, very, very specific region in the world. Maybe the validation over your region is not as good as would be.
The accuracy, right?
In your case, could be interesting to make a study of the validation, but in general terms, yes, they are validated.
Okay, and maybe one last question for the moment. Is it possible to use Jupyter Hub CMEMS to download data aggregates? For example, can I download daily mean winds from the hourly product? This one, wind globe physics.
Well, as I said before, yes, there is a possibility, but it depends on the product. I don't know specifically in this product. Wind global physical analysis, L4. This is a multi-year. This is an L4, so it is data from satellite, and I don't know specifically for this data. But as I said before, you have, for every product, you have an ID, a product ID, which is the ID the user has put here, wind glove, physical, L4, etc. And the data sets, when you go to the data store, the Copernicus data store, you have to define also the data set. And most of times, these data sets consist on different levels of aggregation. You can probably find daily data and monthly data, even annual data, etc. So in this case, I would go over the web page. We can we can do it on on the fly, but I don't know.
Yes, of course. Would you like to show that, or
Wind glove. Well, yeah.
as you want? If you think it would be very time consuming, or if it could be easy.
Thing. Let's try to find in Ocean Products. Enter to the Copernicus data store. Come on. I think the product was wind glove P L4.
Yes, it already gives you
We don't know
the
if
options.
it was a multi-year product, right? It was.
Yes.
Oh, well, you enter into the product and use downloading. You can see here the data set, and this data set usually includes the levels of aggregation. Both of them, both data sets, well, in this case, the both data sets are hourly data, one hourly. But the difference between both data sets are the resolution of each one, right? So this is the only level of temporal aggregation. You only access different resolutions. Well, but at the end, in other products, these different data sets includes different levels of temporal aggregation, like daily data, monthly data. So,
okay, great. Thank you. And now we don't have time for any more questions now at the moment, because we will have a second tutorial also given by Alvaro. A little bit more advanced. So now we're going to go into a little bit more on the data side, right? So first we had a little bit of an introduction to Python. Now we're going to go dive a little bit deeper, almost literally diving.
Yeah, yeah. This is
Okay, the floor is yours.
More specific. Can you see my screen again?
Yes. Shall we try to put it in full mode, full screen? Can you try? Yeah, would that work for you, Alvaro? Do you think?
Yeah, fine.
Okay.
It's too small, the letter. Maybe I can try to.
I mean, for me it's fine, but I've had some comments. Yeah, we've had some comments, but at the same time, I would advise you to see this in a laptop at least, not on a phone, for example. On a phone will be hard. Okay. Whenever you want.
Now we are going over the second tutorial. This is more specific and more advanced. It has quite a lot of computation. We are not going to talk so much about Copernicus here. We are not going to talk so much about Copernicus products. Actually, we are going to download a few products, and we are going to make computation over the products, right? Well, in this tutorial, we are focused in the problems that in one specific problem, we decide to go over one specific problem that usually affect the ecosystems, which is the case of coral bleaching. You know, this coral bleaching is sometimes produced by some variables like the temperature of the water or the pH of the water. The coral bleaching doesn't directly kills the coral, but it's in a state where the coral is clearly affected by harmful conditions in the environment. So to explain, as I said before, this kind of events are usually associated with the temperature of the water. So in this case, we decide to do some analysis of the event that occurred in the Caribbean Sea in 2005. This event was very important, and it is very well referenced event because there are lots of papers about this event defining what happened in that time, the period of time, the region that was affected, etc. This event affected the eastern side mostly affected the eastern side of the Caribbean Sea, as we will see later. Well, we want, obviously, Copernicus services cannot provide direct information of coral bleaching like these pictures, because this is work that has to be done in the field. But for example, Copernicus services, they can provide information like chlorophyll in the water or temperature of the water that could be good information sources that could give you information about the state of the ecosystem, to evaluate the state of the ecosystem and the health of the ecosystem. As I said before, these coral bleaching events are very related with the temperature of the water. And as you probably know, nowadays, the way we analyze the high temperature of the waters is using the definition of marine heat waves. Marine heat waves are periods of time where the temperature of the water is exceptionally high. Here I have a diagram took from Hockey et al. 2016. You can see here, for example, we have in red the temperatures time series in a specific point, whatever it is. And the blue line is it would be the mean value, the climatic mean value for a specific day of the year, the specific days of the year. And the dotted black line represents the 90th percentile of the climatic variability in this specific day, right? So we define marine heat waves right now in scientific communities. Marine heat waves are defined as periods of, well, we can be bigger, longer than 5 days, or these are parameters that can be modified, that where these periods, the temperature of the sea surface temperature is higher than the 90 percentiles for a period of time. And this period of time has to be longer than a specific threshold, because if it is not longer than a specific threshold, we do not consider this as a heat wave. We consider it as heat spike. It's just a punctual surpassing of the 90 percentile, right? Well, what we are going to do in this tutorial is to download some data from Copernicus services and see what happened in terms of marine heat waves in the Caribbean Sea, in the region affected near Barbados and Virgin Islands. So we want to see what happened with marine heat waves in 2005 in that region, and see if it could have some relationship. Well, according to the bibliography, yes, it has a lot of relationship. There are lots of information in literature about the relevance of temperature, sea surface temperature in that period in relationship with the event of coral bleaching in Caribbean Sea, right? Well, I would say before continuing, the intensity of a marine heat wave can be defined in using different parameters. For example, you can define how intense is a marine heat wave. You can define the intensity of marine heat wave as the maximum temperature. It would be okay. It would be a possibility, but you could also consider the intensity of marine heat wave as the length of the marine heat wave, the time it is affecting. You can also consider the ramp, the ascending ramp of the marine heat wave, as an indicator of the intensity of this marine heat wave. You can also, there is another option, which is the integral of temperature between the cumulated temperature of the marine heat wave from the starting to the end of the period, etc. There are many parameters that we can use to define how intense is a marine heat wave, right? Well, as before, first of all, we have here a cell where we are defining the libraries we are going to use in this tutorial. Not much new in this cell. We are using again NumPy library, XRite, Matplotlib for plotting, Cartopy for plotting maps, and also since we are going to need to work with we are going to manipulate a lot of date formats. We are going to use DataTime library, which is a DataTime that provides some classes to switch between different formats of dates, right? Here I let you some information about marine heat waves, core bleaching, and the events of 2005. Very interesting if you want to follow this tutorial and also improve get more information about this event. Well, as before, we are going to start with downloading the data we are going to need. Well, in this case, we are going to download two different data sets. Both data sets are obtained from satellite data, reprocessed data, L4. They are data, global data, so we have data for the globe. And as you can see, we are going to download data, the same product, but we are going to download two different files of the same product. In one case, we are going to download a file for 2005, and not even full 2005. We are going to download some data for the summer 2005 and use a quite wide window of a quite big window of latitudes and longitudes. And after that, since we are going to compute the 90th percentile of temperature, to compute that, we need a very long time series to be able to compute a robust 90th percentile, right? So we are going to download another data set that goes from 1990 up to 2021. This is 30 years of data. So since we are downloading 30 years of data, in order to keep the size of the file not very big, we are going to download a quite small window, geographical window, so we can go over a specific geographical window, getting a very, very long time series. Well, as I said before, this is the same than before. You can download this data through the Copernicus services webpage, through the Copernicus Marine Data Store, or you can go over to the Copernicus Data Store and in the API request get the information of MotoClient and use these two commands of MotoClient. So you just have to run these two options. Since we already have this data here, I am not going to run this cell. I encourage you to run this cell and see how they work and see how big are the files downloaded and how many time it takes to download it. Well, first of all, once we have the once we have the data downloaded, we have two files. The first thing we are going to do is have a quick view of the marine heat wave, the surface temperature in the Caribbean Sea in 2005. To do that, we are going to open this data file, which is the data file that has all information for Caribbean Sea in summer in 2005. And as before, we open this data file with the XRA function, open dataset, and using the path and the name of the file. And we create an object, ds, which is the object through it we can access all the data, right? Well, as I said before, these files have dimensions, attributes, and variables. This is the data file we have opened. You can see we have 500 latitude values, 800 longitude values, and 62 time steps. And here, as different than before in the previous tutorial, we are only downloaded one variable because we want to keep the size of the file not very big, right? So we have selected just one variable that depends on three dimensions. We are not including here depth because these are data, surface data. And so since they are data from satellites, most of them are surface data, so we do not have depth dimension here. Well, as first example, this is not as much different than before. I'm going to run this cell. We are going to make a plot of sea surface temperature in the region. This plot map function is almost the same function we defined in the previous tutorial. It's a very simple function where we are creating a plot in a specific figure and axis. And this loop is just a loop to create a map, a sequence of map, the movie of how it was the sea surface temperature. You can see we are looping, we are doing a for loop over the ds time. So we are going over every time step, but we are skipping some time steps. As you can see, we are plotting every second value of time step, every second time step. And the people who is related with Python code will know that here we are using different plots. So we are making an array of plots with the different maps, right? For example, here we have for the 15th, 17th, 19th, 21st, etc. And well, we can have a look, first view of the sea surface temperature in the Caribbean Sea and also the Gulf of Mexico. And we can see that, well, at the beginning, the temperature in the Gulf of Mexico was quite high, very high, actually. But with continuing the movie, we can see that in September, we start to have very high values of temperature around Cuba. But looking at the eastern region, that is the region most affected by this coral bleaching, at least according to the literature, we can see high values of temperature, but actually they aren't as high as they appear to be. For example, the values of temperature are higher, for example, around Cuba or here or in the Gulf of Mexico. So what happened? There was a problem here. There is, well, this is because we are defining the marine heat waves, right? Because maybe the absolute values of temperature are not so high here in the eastern coast, eastern side of the Caribbean Sea, near Barbados or near Virgin Islands. But actually, since if you compare these values with the climatology of this region, these values could be really, really high. Well, so how can we solve this? Well, so we can solve this using the definition of marine heat waves. So the definition of marine heat waves, we are comparing the values of temperature, not with in terms of absolute values, but in terms of compared with the climatology of the wave, right? So let's go to an analysis of marine heat waves in Caribbean Sea, a proper analysis, right? So to do that, we are going to open the new data file, the other data file. As this is the other data file I said before, it has a very, very long time record. This cell is, as in other cases, this cell is just a cell to open a new data file that we will call again DS. So we are overclocking the previous DS object with this new file, right? We run this, and as you can see here, we have a file with almost 200 values of latitude, more than 100 values of longitude, but we have 11,000 values, more than 11,000 values of time, because obviously we have here, if we see the report of time values here, we have time values for every day, for the January 1st, 2nd, 3rd, etc. For daily value, we have daily values of surface temperature since 1990, January 1980 up to December 2021. So we have a very, very long time record. We need this because we need to compute the 90th percentile of everyday data in a daily means. So we need to have the longer time period because we are reducing a lot the data with this computation. Well, after this, we are including this cell where we are just selecting a point to work. We have decided to use this point, this location, but any of you can change the location you want to analyze. And I'm gonna run this cell, and while it runs, it takes a little bit because this cell is computing the mean of the data in the dimension time. So we are making a temporal average. We are making a temporal average of the data. So hence we have 11,000 time steps. This takes some time in doing this mean. And well, as you can see here, to compute this mean, we just have to go over the specific variable in the data set and use the function mean with the dimension we want to. So with this function, it's very easy to compute means along dimensions, for example, along temporal dimensions, latitude, longitude, depth. So, and as you can see here, we have to transform our data from Kelvin to Celsius. And well, after this, as you can see, the cell is still running. So as you can see, it takes some time. And well, here in this part of the cell, we are just making a little plot of the mean SST. We are using plot title mean SST. We are doing this kind of plot. You can see here we have the same region than before, but in this case we only see values of temperature, surface temperature for this specific region. As I said before, we had to reduce the window we are working on to reduce the size of the file. And here this X represents the point we are going to analyze in this work, right? You can change you can go over any latitude and longitude, but you have to be inside this region. You can try to download a new data set outside, for example, here near Cuba, and you can download another data set and change the data set you use here. So you can make an analysis of marine heat waves over any region in this window, right? Well, once we have defined this latitude and longitude position, and we go over the cell that specifically finds the marine heat wave events in our time record. Well, what we are doing here is from this data set that has a lot of time steps, we are going to select the time series over this location, and over this time series we are going to make the analysis to find these periods, right? The periods where the temperature is over the 90th percentile for a time longer than 5 days, right? To do that, we use this. Well, we are here. Well, we use this cell. This cell is a little bit tricky. Well, first thing we do is to import a new library. You see, marine heat waves. This library is accessible, open accessible in the Eric Olivier GitHub webpage. Just a second. This is one of the powerful things of Python, that you can find libraries for almost everything you need in web. This library is very famous and very used in scientific community. We thank Mr. Olivier for publishing open his library, marine heat waves. It has other libraries, and here you can find other all the documentation you need to use this library. And well, we have downloaded this library from Olivier GitHub, and we are going to use this library for the computation of marine heat waves, right? So we have here the file. You can see the computation of marine heat waves. This library has the code with different functions. For example, the function detect, which is a very important function here. This is the function we use to detect the events of marine heat waves in a specific time series. And it also has different other functions that we are not going to use here. But as you can see, these functions are quite long and specific. So we do not have time to program this here in this course. So we are going to use directly the function delivered by Olivier. So, well, the way we import a library is very easy in Python. You know, you have a file with the functions you want to use, marine heat waves.py. So to import this function, you just have to import the name of the file without py, and you can use a name for accessing the certain name for accessing the library. And that's all. Since you have imported the library, you can access all the functions inside the library using the name you have given to the library, and access the functions inside, right? So first of all, we import the library, and at the end of the cell, we are going to use, as you can see, the function detect of the library to get to new variables. Well, what are doing here? Well, this is quite a problem in Python. There are many formats to handle with dates. So the thing is, when we we get information or when we get the data from Copernicus services, the XRI library works with a format, uses times as format using called date time 64. It's a format defined in XRI library, but to use this library from my heat waves, we need to transform the format of dates into two different new formats. We need to the dates in as date time objects, which is an internal date format for Python, and also we need date time ordinal object values, right? So this is what we are doing here, convert the time formats. You can see we are defining a function that gets a date in format data times 64, and we transform the format np datetime 64 to a datetime. And we are creating two new variables that are dates in format datetime and dates in format ordinal. So to compute, we get also the values we want to use for the computation. This data mine heat wave, this variable was defined before, selecting from the data set the latitude and longitude points we wanted to analyze, right? So data mine heat wave, maybe we can have a look of what is data. This variable, if we print the report of this variable, we see that this variable doesn't have latitudes and longitudes, and also only has the time dimension. So it has a time series over a specific location, latitude and longitude, which is 15 degrees and -60 degrees, which are the closest points to this requested point, right? Well, we can continue, and with this, we get the SST information from the data set, and we also have formatted or time vectors. So we just have to run the function detect over these two arrays, over these two vectors actually. And well, running this solve, maybe we could have a look. It is still running, but it's finished. We could have a look my heat wave. To this, we are getting these two variables or these two objects that actually are dictionary objects, Python dictionaries. If we print this my heat waves object, we see that it is a dictionary with different levels, with different keys. For example, the time start, the time end. This is a list of the events detected in all the period, all the time record. The first marine heat wave event, the second, the third, etc. So it has, the dictionary has different keys for different parameters of every event. For example, the time starting, the finishing time, the time where occurred the peak of the temperature, the maximum temperature, the date of the starting, which is almost the same, but as I said before, in a different format, the finishing date peak, etc. The index in the time series. For example, it also has the duration of the marine heat waves. For example, here it is in days. So we have events that last for 6 days, and there is also events that last for 75 days, and also 100 days, etc. Duration. Well, we have many parameters inside this dictionary. I'm gonna remove this. And once we have this information of the events, we can start to work. We can start to see what happened in 2005, right? So for example, we can start to make some reports of what happened in 2005. So we can define a period of time, for example, from the beginning of 2005 up to the end of 2005. And in this cell, we are just selecting the events that occur in 2005 with using the function where from numpy. It's a very useful function to select elements inside an array. The elements that has the specific conditions. For example, we are selecting the elements in that where the marine heat waves, the starting period was less than this date end value, and the finishing period time is higher than the start period, right? So we are selecting the elements in marine heat waves that the array, the vector of marine heat waves that started in the period 2005, right? And after that, we have just a loop that goes over every event, writing a short report with showing the maximum intensity, average intensity, cumulative intensity, duration of the event, date of starting and date of finishing date. And you can see in the period 2005, we have found in this location 4 events with these specifications. One of them lasts for 10 days. The first one lasted for 10 days. The second one lasted for 92 days, 23 days, and the last one lasted for 75 days. Well, this report is interesting, but maybe it's better if we can plot something so we can see what happened in this 2005. So to do that, I did this cell where we are plotting. We are making a plot very similar to the one we saw before, but you can see here we have in blue the line of the climatology. This is the mean, the temporal daily mean of the values. In black, we have the temperature of sea surface temperature observed, and the green line is the value of 90 percentile of temperature, and the shaded pink shaded areas are the areas detected as marine heat waves. You can see here that clearly we have the first event, the second event, that it was about 92 days, the third event, and the fourth event. We can see here that, well, despite of the literature focus on the coral bleaching event in the Caribbean Sea, in the region that occur at the end of the summer, we can see that actually in that year the temperature of the sea in that period, in that location, was really, really high, almost since the beginning of February. So maybe the coral bleaching event, we could study if the coral bleaching event was not affected as much for the high temperatures in summer, but also for the sustained high temperatures all along the year. And we can also see that there is a peak of temperature near May that occur here. That is a very, very, very high value of temperature that occur in spring, early. In that we could analyze if this peak could have something to could have a role in the process of coral bleaching that occur, or that is described at the end of the summer. Well, once we have this is interesting information. So from here we can start to continue with our analysis in different. We can get some conclusions and continue with our analysis. But we can also analyze other things. For example, since we have the list of marine heat waves in the full record, we can analyze the full time record and see what happened and see what the record of marine heat waves along for the last 30 years, right? So to do that, I did this last cell. You can see here, first of all, in the cell we are defining a new function that is just a function that, like as we did before, we define a function to plot maps. Here we are defining a function to plot histograms. So this is a standard function that we have called bar plot, and we use the data in X, data in Y on the title, and the label in the Y axis. So, and this only creates a figure with axes, and only creates. Let's run this and let's see what it does. I think it's simpler. That creates a histogram where every line represents a marine heat wave event. So we can see the events located over the time record. And also we are plotting the maximum event. For example, as you can see here, we run the function bar plot for using the duration of the event, the maximum intensity of every event, the cumulative intensity, and for every histogram we are plotting in red the maximum event according to this parameter. As I said before, we can define. There is not an agreement of what defines the intensity of a marine heat wave. We can define the intensity of a marine heat wave according to different parameters. For example, we can think on the intensity of marine heat wave as its duration, or we can think of the intensity, about the intensity, taking in consideration the maximum temperature or the cumulative temperature, etc. Right? So we are doing this. We are using the bar plot to plot different parameters of intensity in marine heat waves. So as you can see here, in the three plots we obtained, the lines are the same in every plot. We have the same events. We are now analyzing the same events, but the intensity of each event could be defined in different ways, right? For example, we see that, let's focus in 2005, which is the year we are interested in. We can see that in 2005, we have few events. As I said before, there are 4 events with quite high duration. with a maximum of intensity that is clearly outstanding in our time series, and also with the quite high values of cumulative intensity, right? So clearly, the year 2005, it was a year with a strong affectation of marine heat waves. But if we look at the red lines, we realize that actually in 2010 we have the maximum duration of a marine heat wave. There was a marine heat wave that has lasted for more than 100 days. And also we have the maximum of cumulative intensity in this marine heat wave. So we could think, okay, 2010 is also a interesting year to analyze in these terms, because probably 2005 is very well described by bibliography, but maybe 2010 occurred something very strong that we do not have information about it. And I think it's also interesting to see the period 2020, the year 2020, where, as you can see, there is accumulation of events really high. They are very, very close. All the dots here are very close. So maybe it would be interesting to go over 2020. In this case, and just to finish the tutorial, I want to go to go over the year 2010, and see what happened in this year, right? So we can go back to the cell where we are defining the period we want to analyze, and we can change the period we want to analyze. For example, we can change 2005 by 2010. And run again the cell, and since in the 2005 we have 4 events. In 2010 we detect 6 different marine heat waves, and we can plot this result in the plot we did, in a similar plot that we did in 2005, using this cell, running again this cell. So, well, this is what we have. As you can see, 2010, it was almost as impacted by marine heat waves, as it was 2005. You can see that in 2005, actually, the high values of temperature started not in February, but even in January, in the middle of January, we started to get high values of climatical values of temperature that lasted for all the winter and all the spring until the summer. So, well, it could be interesting to go over this period and see what happened with corals, and we have some markers of how to detect periods of time that could affect the health of the ecosystems in Caribbean Sea or in other sea over the world, right? Well, this is the tutorial. I think as last in this tutorial, we have seen how to download data and use the data, and also use external functions, Python functions, to make computations. As I said before, at the end, the most of the work can be done after you download the data. You can download the data from Copernicus services, and after that, you can make lots of computations and make lots of statistics to get the conclusions you need. As final exercise, I proposed this because, as I said before in the beginning, we had very, very high values of temperature in the Gulf of Mexico, for example, in this period in 2005. So maybe it could be interesting to go over the Gulf of Mexico in this period and see what happened this year in the Gulf of Mexico. So I propose to do this, since we do not have in this file, we do not have information about the Gulf of Mexico. We have to go back to the beginning of the tutorial and start downloading the data we need to analyze the Gulf of Mexico, right? So we have to download a specific region in the Gulf of Mexico. And I propose this location, 27 degrees and 80 degrees west, but you can go to any place you want. So you can download this data and run them all, and run all the cells, adapting everything you need, related in latitudes, longitudes, etc. And well, this is, I think, quite interesting exercise that could give you information of how to work and compute marine heat waves.
Yes, thank you, Alvaro. We hope this was a very interesting tutorial for you. As we said, as you've seen through Alvaro's tutorial, this is a little bit more specific on the data and how on a study specific. I find this one very interesting, particularly. So we hope you can, if you were not able to follow along to do it on the site, just don't worry, you will be able to practice it. To practice on your own later on, once you can have access to the Jupyter Hub.
Yeah, I think it's interesting to go slower over the Jupyter Notebooks, reading everything and taking time to see the code and everything. At the end, the code is not as, if you are familiar with Python coding, this code is not as complex as it could be in a first view. But obviously you need to go slow,
step by step, right? Yeah. Yes, but it's already good. I think that the participants will have the chance to see the replay of this session, and then we'll have your explanations, right? So they can go back and have the explanation for each line, for each code line. Okay, so we have time for one or two questions. The first one, is there available repository of existing data on heatwave analysis and forecast free for download for research purposes? In Copernicus,
if any university would provide this, but as far as I know, there isn't. You go with these tools, you can go over the region you are interested in, and as you can see, you can have the full record of the marine heat waves in the region you are interested in.
Yeah, you kind of have to do it the separate download yourself, right, of the parameters you need, right? Okay, second one, if I'm downloading temperature data, different depths, what is the command to show a specific depth? I don't know if you showed that one during
the thing is, can I share my screen a little bit? Or
yes, sure.
I think it's better if I can show it. Well, I think I'm sharing my screen right now.
Yes, we can see.
The thing is that, as I said before, in this example, we are not downloading data from, we are downloading data from satellite data, so they are sea surface temperature data. They don't have depth. For example, you can see here there is no depth inside. If you want to work with depth data, it's better to work with data from models. That models provide information of depth. You can see here in the previous notebook we did. For example, we downloaded data from the global analysis model. Here you can see, for example, in this comment, that in the first tutorial, there is some parameters that specifies the depth you want. For example, you can put here from 0.5, which is surface, up to 100 meters. And go ahead, and surely this will download depending on the size of the file, it could be a problem. But well, this
Yes,
will download the same data, but including
but
all
the specific depth, is it? Okay, interesting. So now we're going to have Stefania Ciliberti, who's going to show you the same data analysis, but this time on QGIS. So,
hello everyone. Thank you, Andrea. Welcome to this second part of our training session that will be devoted to introduce the QGIS training, let's say exercise about the scope of this training that is assessing the ecosystem health. So this training is organized in two parts. The first part basically will follow more or less the track previously defined by Alvaro in presenting the coral bleaching event occurred in 2005 in the Caribbean Seas, mainly using model data. And the second part is instead trying to focus much more on the nowadays. So what happened in the last July, that was the record-breaking month with prolonged and intense marine heat waves in many places in the world, and particularly in the Caribbean Seas. That was quite, let's say, affected by this type of events with consequent damages and dramatic impacts in the ecosystem health. But now let's start with our exercise, so focusing on the first part, and as has been, let's say, described in the, so basically, let's open, first of all, the QGIS software. You have all the instruction in the user guide where it was, let's say, described how to access the link and how to configure the plugins that we are going to use. And the first step, of course, that I recommend is to save your project in a working directory that you can find in your laptop. And for instance, I have created a dedicated folder where I'm going to save all the results, and I save the project with the name, for instance, projects. Okay. So now that the project is saved, the first thing we do is to import through the server, base map server that has been downloaded in the before, the plugin that has been configured and described in the user guide. Let's load, first of all, a base map that will help us in also, let's say, focus on the region of interest, that is the Caribbean Sea. In particular, we will have a dedicated focus on the eastern part, particularly. And as has been described before, and also yesterday during the first part of the training session, Copernicus Marine Service offer a wide catalog of product that covers particularly the global ocean. And now we are going to use, first of all, to characterize the area of interest, we are going to load the bathymetric data that is provided by the model product, that is the Global Ocean Physical Reanalysis. We decide to use the reanalysis since this is a let's say, high-quality product provided by the Copernicus Marine Service for the Global Ocean from 1993. So it covers also the period that we are interested to analyze, that is particularly the 2005. And as described in the user guide, you might have different ways to access the data. Particularly, bathymetry is one of the dataset that is accessible through FTP. So when we use the CMEMS NetCDF plugin installed, pre-configured in your QGIS software, you can open your file that is located previously, let's say, downloaded. And the first thing is to add the bathymetry as an additional layer in your QGIS environment. So we add depth O, that is the standard name for the bathymetry. And we basically can see that it appears in our canvas, in our main window, let's say, for the whole ocean, the whole global ocean. Of course, our interest is very, let's say, limited on a specific region. So the first step is to, let's say, configure the bounding box that will be basically the region where we are going to work. To do this, we need to create a layer. This layer is created by accessing the layer menu and adding a new shapefile layer. This new shapefile layer, of course, will be saved in your working directory. For example, let's call this shapefile as bounding box, bbox, and we save it. Once it has been, let's say, saved, QGIS requires also the specification of the geometry type. In our case, it is a polygon. And the rest of the settings can be left as they are by default. Once we do OK, in your left side, you see that the bounding box is now as shapefile created, and we are ready now to use it. To activate, you can easily go through the toggle editing in the top menu, that is this pencil, that activates basically the shapefile. And once activated, we can add the polygon feature by clicking to this icon that opens a sequence of additional subfunctions. In this case, we are simply interested to digitize a region. So we select digitizing shape that gives to us the opportunity to draw any type of geometrical feature in our map. In this case, I want to use a rectangle from extent because I can fix, for instance, a point as I'm doing like right now, and I can draw my rectangular. And for instance, we can consider this rectangular as an example. We prescribe an ID that is automatically given by the QGIS. And once we are happy with this, let's say, shape, we simply deactivate the toggle editing that asks you to save the result. Once done, we can, for instance, modify the properties just to give some more clear look and to have also control on the map. And this is basically the final result. So now we have the two elements that we can use for, let's say, clipping the bathymetry in our target region. And to do this extraction of the bathymetry in the target area, we can easily do raster extraction, and we can clip raster by mask layer because we have the mask layer basically defined in our bounding box. So the input layer will be the bathymetry, the mask layer will be our bounding box. The rest of the settings you can specify or not as you wish. I mean, they are optional, but what is important is to save the result in a file. In this case, let's go in our working directory and we save the result as bounding box bathymetry. For instance, we give this name to our file. And now that we have defined where to save the result, we do simply run. And as you can see, the map of the bathymetry cut in your bounding box appears quite nicely. And of course, we can modify the symbology of this layer by changing, for instance, the render type. We can use the single band pseudo color and specify which is the minimum and the maximum value of the bathymetry that we want to visualize in this area. For instance, I want to use as minimum value 10 meters and as maximum value 5,000 meters. And as color ramp, I would like to use this one that is Mako, and with the invert color ramp in order to give lighter color to shallower zone. We can even modify the palette, the interval of our palette and the precision of the labels. I mean, this is something that you can explore, but at the end you can easily, let's say, change the shape of your region, and you can see much more clearly the gradients and appreciate the gradients of the bathymetry that you have in this zone. Now that we have, let's say, identified the bathymetry in the region, of course, we know that the coral reefs that are particularly present in the Caribbean Sea, being one of the richest site in the world that contains around the 7% of the coral reef available, I mean, present in our planet, we know that they are, let's say, located, distributed in a region that might be up to 400 meters depth. And so for this specific scope, we can exploit the QGIS features in order to extract specific information, spatial information in this area. To do this, we need to reclassify basically we need to reclassify this bathymetric file. And to do this, we first need to convert this from raster to vector. The vector, of course, will embed all geospatial referred information in each grid point. To do this, we go then to the raster menu, we open conversion, and we select polygonize raster to vector. We decide to have as input layer the bounding box bathymetry, so the bathymetry defined in our bounding box. And we save the result in a file that, for instance, called bounding box bathy 400 meters. Okay. So in a new shape file, so that can be easily reused later on. And we run. Of course, it might take some time, depending also on the extension of the region or the, okay. We close, and as you can see, we moved from a raster file, that is this one, to a vector file that is, let's say, represented in this way. Having now each grid point with a specific, let's say, geographical information embedded, we can easily perform a filtering of this object by selecting the shapefile, doing a right click, select filter. And now the field that is named DN by default, but of course you can even change it, but in this case it's called DN. What we are interested to do, basically to filter out all the grid points that are deeper than 400 meters. So we retrieve only the values of DN that are higher than 0, and lower or equal than 400. And as you can see, automatically you have in your bounding box only the grid points that are related to this type of query, basically only the region that have a maximum depth of 400 meters. Another nice functionality of QGIS is the fact that you can even extract information on irregular shapes or regions. And for instance, if we want to have a look on what are the physical parameters that we are going soon to load in our QGIS environment, but only for a specific portion of our domain, for instance, in a region that include Cuba, Dominican Republic, and Puerto Rico, we can again create a region and try to elaborate this information and embed this information given for these grid points in your target area. So again, we need to create a new layer, a new shapefile layer. In this case, we give, we save, of course, all the time in your target, in the target working directory. This is somehow recommended because if you save, as I was doing before, directly typing the name in the window, you basically are going to store this type of information in one of the QGIS internal folder, and that might be quite complicated later on to recover. So I recommend all the time to use a reference folder for managing your information, your project. So we gave this name, region, for instance. Again, this is a polygon. And exactly as we did before, we activate this shapefile, adding a polygon, a feature polygon, so selecting this icon that basically help us to add the polygon feature, but this time, instead of digitizing a shape, I want to digitize the region with segment. So in this way, I am free to create the shape I want for regrouping the region where I want to, let's say, concentrate my attention. For instance, this one. I give an ID to this region, to this shapefile, and you see that it appears on your map. And once we save, basically the control is again on you. And now the point is what we want is to extract the vectorial information only in the region that we have been right now defined. To do that, we use a function, being the source, a vector. We need to inquire the vector map menu. So we use the geoprocessing tool, and among them the method intersection. As input layer, we give basically the bounding, it's the B-box bathymetry at 400 meters. And as, let's say, overlay layer, the region, okay? Then the rest should be basically leave as it is without any problem. We save the file here and we call it region 400 meters, for example. And we run. Okay. Once finished, you see that basically the scatter, these grid points that are like sort of scatter are colored differently from the previous one, from the ones that are inside the bounding box, meaning that we achieved our objective simply to taking only the grid points where we want to focus the analysis. And now, in order to use this data structure for further elaboration, we simply need to merge all these points. And to do that, we again inquire the geoprocessing tool, and we use the function dissolve. The function dissolve is applied to the input layer that is region 400 meter, and we create the new file that we call dissolve region 400 meter. We save it, and once done, we run. After that, as you can see, here you have basically the shapefile that is now a unique object that can be used exactly at the same level of the bounding box of a regular geometry. Now, after doing that, that was our preliminary step, we are ready to load the physical files provided by the Copernicus mining service in the area. In this case, for example, what I want to analyze is basically during the 2005, and particularly when the hotspot of the marine waves has been, let's say, identified in 2005, also as was shown before by Alvaro, what I want to analyze is the value of the anomalies of the sea surface temperature in the region during the September 2005. But on the other side, I would like also to analyze what is or what are the values of the bottom temperature in the same region, so up to 400 meters. What is the temperature that the reanalysis model data have simulated at the bottom level, at the topographic level of the seafloor, in order to understand how, let's say, the increased of sea surface temperature in the region might have impacted also in the bottom topography. So the first thing that I need for computing the anomalies, I need a climatology, and in this case, again, we access the climatological fields provided by the global ocean physical reanalysis as given by the Copernicus Marine Service, preliminarily downloaded, and in this case, I take the one for September 2000, so for the month of September. So the climatology, of course, is computed over a longer time series that in this case goes from 1993 to 2016. Okay, in this way, the CMEMSnet CDF plugin gives to me the list of variables that are contained in the region. So first of all, I want to add theta O, that is the standard name for temperature. In this case, I have, as we will see, okay. As you can see, being these climatological fields downloaded from an FTP, they are provided for the whole global ocean and for all the depths that the global ocean reanalysis is, let's say, representing in the model. In this case, I want only the temperature at the surface layer. And for instance, I put this file in a dedicated group that I call upstream. I do basically the same. As you can see, it appears in your map, in your board, let's say, of QGIS, but I want also to add the bottom temperature. In this case, I select, being a 2D file, the bottom temperature. Again, it's the temperature, remember, it's the temperature that is available at the seafloor. It is a 2D data structure. Of course, it's a climatology, and I add this in the same group that I created before for the temperature. So I have loaded the climatological fields. Now I want to load particularly the monthly mean, that in this case, again, have been taken by the from the global ocean physical reanalysis of the Copernicus Marine Service, this time downloaded through the Motu client, so in a specific bounding box, as I'll show you. And again, it shows the temperature. In this case, I have been downloaded only the surface layer. I select the September 2005 at the depth of 0.49 meters, and I put this layer under the upstream group. And I add also the corresponding bottom temperature field. Be careful all the time that if you are loading multiple files on the same group, do not overwrite the group, otherwise you will lose all your work. So you see here basically that in our bounding box we have information for the bottom temperature and the temperature provided by the global ocean reanalysis for September, that is in this smaller bounding box. While in at level of the global ocean, we have the climatology that we have been computed before. Now, what we want to do is basically to, let's say, extract the information of these fields for both climatology and monthly means for September 2005 over the region that I have been defined before. So only in the region where the bathymetry is higher than, in the sense that we are taking the bathymetry from 0 to 400 meters only. To do this, we can use basically exactly as we did before, the raster, and having all raster files, we can extract simply this information by taking through the raster menu the function extraction, and we clip the raster by mask layer. But this time, instead of doing one by one, we can exploit the batch processes provided by the QGIS. So as input fields, as input layer, doing basically clicking on autofill and selecting from open layers, I'm able to select exactly the fields that I want to process, that are the bottom temperature and the sea surface temperature, in this case, for the climatology and the monthly mean. As mask layer, I want to use the dissolve region at 400 meters, so the unique block that identify my target region, and to apply to the rest of the layers that I have loaded before, I can do simply a fill down, and automatically to each field, the corresponding mask layer is associated. The rest you might leave as they are, since we don't want to specify anything else. And now we can save the result, for instance, in our target directory. We prescribe a tag of the output file that we are going to generate, for instance, region, because these are basically the fields that we are going to retrieve in the region of interest. And another nice function of QGIS is the fact that it gives to you the possibility to autofill the file name of your layer by, for instance, the parameter values. That is what I want. I want to use basically the file name of my input layer to complete the result. So the final layer name that I'm going to store in my working directory. So in this case, the result will be saved in these layers. Once you have done this, you can also load the layers when they have been completed. And now let's run. Okay. Now the process has been complete. Let's see the result. You can see here that basically, even if in color gray, you have here the values of temperature from climatology and monthly mean for temperature and bottom temperature. And now what I want to do is to compute the anomalies for respectively sea surface temperature and the bottom temperature. This is now extremely easy because we can use the raster calculator. And in this case, by simply computing the difference between the in this case, the September 2005 bottom temperature and the climatological field that I have been loaded as well before, and saving this result in a dedicated file that, for instance, I can call bottom temperature anomaly. The calculation is complete, so I have been computed the such anomaly by taking in input the fields that I have preloaded before, and I do the same for the temperature. So again, to compute the sea surface temperature anomaly, I subtract, of course, for September 2005, I subtract the temperature, the monthly mean for September 2005, and I subtract basically the climatological field. And I save this again in a dedicated file that I call SST anomaly. Of course, all these intermediate fields that you have been created, like the temperature and the bottom temperature in your region, you can also modify the symbology in order to make it more, let's say, easy to be read. For a matter of time, I don't spend, I mean, I'll not go through it, but you have the details, or you can ask if you have doubts about the information that have been provided in the user guide. But here it's nice to see the result of our computation. So here I'm analyzing the sea surface temperature anomaly. In this case, I can, for instance, specify the single band pseudocolor. So I want to visualize the anomalies between -0.5 and 0.5, using a color ramp more appropriate, for instance, the one that is from red to blue, even if I have to invert in order to give the blue colors to the negative values. So this is applied here. And now for the bottom temperature, as you can see, we have already quite, I mean, the magnitude is quite different. We have much more, let's say, spread in the values. We go from -2 degrees to 1.5. So these are somehow values that might be an alarm for the coral reef, because it defines conditions at, of the temperature at the bottom topography, where the values of the temperatures are higher than 1 degree. That usually is the threshold used for monitoring the level of risk for the coral bleaching in any region where coral reef appear. And again, as we did before, we can prescribe, for instance, the minimum and the maximum. Just let's give some, let's say, more restricted interval in order to see better, a bit better, where the higher and the lower values are located. So here you see that, especially in the region quite far, I mean, here we are in the shallower region, so the bottom temperature anomaly is, let's say, or the sea surface temperature anomaly is warmer than the anomaly of the bottom temperature in most of the cases, but there are some spots where the anomaly of the bottom temperature is even much higher than 1 degree. And so these are values that might be monitored, and together with the sea surface temperature anomaly considered when you are facing some dramatic marine heat waves event in the region. And there are some recent studies that are trying to correlate these two variables in order to, let's say, also, and I'm connected also on one of the questions that I saw before in the chat. It's important also to understand what is the value of the temperature along the water column in order to better represent the potential, let's say, problems that the coral reef might experience during a heat wave event, because this parameter, the temperature along the water column, might impact quite dramatically on the productivity and organization of the demersal species in the region, and also, let's say, cause some problems in terms of bleaching, and might be quite a threat for the biodiversity and also for the ecosystem health in the region. So these exercises show you, of course, how to manipulate, how to access information from the models that are very powerful. And QGIS can be used also for extracting specific, let's say, statistics in the region. I'll invite you, for instance, to access to one of these functions, that is the raster layer statistics. This raster layer statistics, if you provide any layer, for instance, temperature and salinity in the region of interest, it can give to you basically a summary of the major statistics like mean, maximum, minimum, standard deviation, and so on. So try to do by yourself in order also to take a feeling about the values that you are, let's say, considering that the model is giving in this specific region as a summary, let's say, to identify some key numbers to monitor in the long term. Now, the second part, and I'll show you quite fastly because we are running late with time, is basically to let's say, exploit the amount of information that we have nowadays, in this case from satellite observations. And in particular, I decided to propose you the event or the what happened in July 2023 because it was quite, let's say, important month in our in this year, because it was recorded as the record-breaking temperature in many places in the world, and these events are causing quite stress to the marine ecosystem at all. And in this case, of course, to evaluate the anomalies of sea surface temperature for July 2023, we might need to access, as we did in this case, a climatology for a longer period as available in the region, in this case from observations, but since we, I'll show you the methodology, the approach just for 1 month, but of course, you are free to elaborate, to download the observational dataset for the sea surface temperature from satellite, particularly the L4 data, in order for a longer period, in order to compute a proper climatology that will be used for calculating an anomaly. So, let's try with this, let's continue with this exercise. And in this case, as I was saying, I want to use this time the sea surface temperature data. Again, I want to compute some anomalies, and for doing that, instead of using any climatology, I refer to the monthly mean of the year before, of July 2022. Just as a matter of, let's say, to show you a bit how QGIS can work in a more, let's say, extensive way. We can select basically all the days of July 2022 by clicking to one of the fields and doing shift. In this way, the files are automatically, let's say, loaded. And they are assigned to a group that is called analyzed SST. That is the standard name for this variable. This is the sea surface temperature at midnight, provided by the Copernicus Marine Service, Sea Surface Temperature Thematic Assembly Center. The values are provided in Kelvin. And what I want to do is to compute a mean, simply a mean. To do this, I basically use a dedicated function that is called cell statistics. So in this way, I can select the days for which I want to compute the mean. Of course, I deselect the layers that are not part of this calculation. And you can decide among a list which statistic you want. In this case, I want simply the mean. This can be, again, I recommend you to compute a proper climatology, downloading all the available data in the region for a longer period and compute the mean as I'm showing to you now. I save the result to a file. For instance, I call this min 2022-07, and I save. And now, once I have provided the name of this layer, I do simply a run that is quite fast. And here you can see the min of the, let me uncheck on this. Okay, we have the min of for July 2022 for the specific region that I have used for downloading through Motu Client the sea surface temperature fields. Now I want to compute basically how the sea surface temperature has been increased or decreased with respect to this min that I have been computed, taking into account a specific week of July 2023 when we were in the real moment in the hotspot for this marine heat wave. So again, I need, in this case, the sea surface temperature files that I have downloaded for July 2023. I add again this layer. And for instance, among the 1 month of data that I have been downloaded, I want just to take, to focus my attention in the week 9 to 15 of July 2023. And I do add and close. I'm basically appending these files in the same group of data that I have been defined before. Now, what I want to do is basically, again, to clip this type of files that I have been downloaded just right now in the region of interest, but this time I present the approach from another perspective, that is the graphical modeler. The graphical modeler helps basically you to organize the workflow of operations that you would like to implement in your QGIS. Instead of doing them routinely one by one, as I did before, this can be done at once. And basically, this tool works by abstracting, which is the specific operations or set of operations that you want to perform. So in this case, for instance, I have what I want to do is to extract the information of sea surface temperature as observed from satellite in the region of interest that I have been defined before, just simply taking the nearest values of without doing any interpolation, just at the location of the grid points that I have been defined before in the region of interest. So I need the raster layer that I call raster, and I need to define the object that is basically representing the vector or the vectorized information of my bounding box. And in this case, for instance, is region. I call it region because it's a polygon that I have been defined before. Now, what I want is to use a specific algorithm that in this case is the clip raster by mask layer. So in this case, as input, model input, I give the raster. As mask layer, I give this generic object that is the region. I use, this is important, we need to, this time to specify which is the projection of that we are going to use. I even specify the target one, even if it's optional. And at the end, sorry, another, okay, I have done everything. And now I want to save the result in out. Okay, so in this way, basically, you have the input data, the upstream data that is your raster file, in this case the SST, the region that in this case will be the bounding box in Cuba, Dominican Republic, and Puerto Rico, where I want to cut these values. And in output, the procedure is going to save basically the information. If everything is correct, I can run as batch process. So in this case, as layers, I want to take just the 5 or the 7 that I was saying before. Oops. So I have a mix now between 2023. Okay, let's use these 3. I remove this. As a region, I take the dissolve one, so the object that is, let's say, continuous in the, that is embracing the whole region, and I do fill down. And as output, I call it, for instance, out. Again, I can use an autofill setting by filling with the parameter values. That is, in this case, the name of the raster file that I'm going to load and to process. And once I have done, I load the layers on completion and I run. Okay, let me now deselect of this because we are not needed anymore. And I guess that I have something else below that is okay. Okay. So now I have computed basically the sea surface temperature in the region of interest. Of course, in this case, they have been computed, calculated, I mean, they are provided in Kelvin. Now, just to conclude, in order to compute the basically this sort of anomaly, I need to cut the mean that I have been computed before by using this dissolved region 400 meters. So I take the previous field that I have been computed and I provide the same information on the target region. And I save it to a specific file. For instance, region mean 2022-07. Simply doing a raster extraction. I mean, being just one file, I can do easily like that. And now I'll do just again the example for one day because we don't have time, but you can continue, of course, the exercise. And what we can do is to compute, for instance, this sort of anomaly of the 12th of July 2023 with respect to the mean of the sea surface temperature computed here before for July. And I call edit region mean. And I save it here. This can be done again with a graphical processor by defining a workflow. What I have done just for one file can be, of course, done for, let's say, for many files you have, like here. And once they have been computed, we can easily, let's say, identify. We know that the regions where we might have much problems or that might be monitored somehow are the ones that can be a damage for the coral reef are the ones that are experiencing temperatures that are higher than 1 degree. So in this case, by simply modifying the symbology of our anomaly layer, so using a discrete interpolation and, for instance, 3 intervals where we define 3 classes of values that are below 0 or between 0 and 1 degree or higher than 1 degree with a better, let's say, color map, with green values where usually the temperature is lower than 0 degrees, and we apply. We can see basically, we can have a view on which are the regions that in the recent period, in July 2023, have been experienced temperature that are higher than 1 degree. And that usually are this is somehow the approach that is used extensively for, let's say, basing some monitoring tools on coral bleaching events for instance, in the Caribbean Seas. Of course, literature gives much more wider and deep explanation on how the methodology should be implemented, because as I was mentioning to you, we need to access a longer time series for computing the climatology, taking the maximum temperature that has been recorded in the region in order to compute this type of anomaly. But this is an example on the way quite easily with the QGIS, we can manipulate satellite data in the region and try also to map which are the regions that deserve much more attention and might be affected by high risk of coral bleaching. Of course, the same, let's say, type of information can be cross-linked with, for instance, chlorophyll data. And recently, the Copernicus Marine Service, as you have heard also yesterday, have been delivered a very high-resolution coastal data set for biogeochemical variables at 300 kilometers. That is, I encourage you also to download and try to, let's say, process in this way. I mean, specific regions that are, let's say, constrained on some specific depth, where usually we encounter coral reef, in order to see how the concentration of chlorophyll has been changed during the event, and try to build some indicators that might correlate the presence of high temperature in the region, so the sea surface temperature, with the bottom topography and with the chlorophyll data, in order to monitor also from a biogeochemical point of view, what is the impact in concentration of chlorophyll and other phytoplankton variables once we are experiencing a marine heat wave and consequently a coral bleaching event. So that's all from my side. Thank you very much.
Thank you very much for your tutorial. I have seen we already have some questions for you. First question. Okay, would it be possible, this is a more general one, I'm sure it is possible, but well, it's not the focus of this workshop today, but would it be possible to import data from CAD and NASA winds to QGIS, as far as you know?
Yeah, I mean, I know that there are some files, I mean, that are provided. I honestly never used, but if they are in NetCDF format with the Siemens plugin, NetCDF plugin that has been developed specifically by the Copernicus Marine Service for this type of training, you can try to load, but surely QGIS provide you also some additional libraries for loading NetCDF. But the same approach, I mean, can be let's say,
Applied to other
type
projects.
of data
Yes.
sets you have, you can.
Mhm.
Honestly, I don't know. this,
Yes, you don't have personal
but,
experience.
But
No, of
if
course.
you are at CDF, in theory, yes. I mean, you can play and see.
Okay. Next one. Is it also possible with CMEMS plugin to elaborate different parameters at the same time? For example, temperature, salinity, etc. Yeah, we were speaking about this in the beginning, right?
We were commenting before, Andrea and myself, about this because it's can be, and it's in the plan of the developers of the Siemens NetCDF plugin to expand the capacity of this tool in order to perform multiple loading of the variables and also of timestamp, because it might be quite useful instead of, as I was doing before, loading one by one. If you have more than one or two variables that you want to load from NetCDF, it might be a bit complicated just to manage manually. Not impossible, but it can be time consuming. But it's in the work plan of the Siemens NetCDF plugin developers, and I guess that Andreia will announce us once the plugin, the next version, will be available with these functionalities.
Yes, exactly. Is in the plans to add this feature, so it's in the pipes. So next question: can this data integration from Copernicus to QGIS be applicable to ArcGIS as well?
Yes.
This is a common question. Yeah.
Yes. So we are using QGIS because it's an open source and providing many support, but of course, I mean, by the community being an open source software, but surely also ArcGIS you can use it. The functionalities might differ a bit, but the most important thing that I want to stress with this training is the fact that it's important to understand which is the workflow. Then the tool, any tool can handle it somehow once you have learned the semantic, the way it works and so on. But in principle, it's important to know that through QGIS, you can even, let's say, improve the way you are doing some spatial analysis. Today, I show you some few examples, but you, let's say, can invent whatever you prefer with the Geographical Information Systems tool, because you see how powerful it is.
Mm-hmm. And one last question, maybe, is QGIS faster under Linux as compared to Windows? I don't know if you have that experience.
Well, I'm not an expert on operating systems, honestly. I'm using QGIS in a Windows machine, and for this type of exercises, it's quite
it's okay.
Okay, yes. Then, of course, it depends on the type of implementation that you want to do. For instance, if you plan to have much more complicated graphical modelers, as the one that I showed you, on areas that are wider, you might face some, of course,
more spatial resolution could be a bit more complicated.
Exactly, on the computing resources or on the capacity of the QGIS tool in the machine. But the nice thing is that you can, even if you have a Linux machine, and I work with a Windows, you can do basically the same exercises and even try to make them more and more sophisticated also in your machines. It's not a problem. Of course, if you have some specific questions that you might encounter during your when you redo basically these type of exercises, and you have some problems, feel free to contact.
Yes.
Yeah.
So about that, there was actually a question. There is on the Padlet, you will find a tab dedicated to any questions. So the idea of this tab is exactly for you to post your questions during your practice. So we hope you will download these tutorials, will rewatch these sessions, and you will practice on your own. And if you encounter any doubts, you can post it there, and we will forward it to Stefania and Alvaro, who can maybe answer it.
These are, in my case with QGIS, these are just examples on showing mainly what are the capacity of the QGIS. Yeah. But you can even refine much more the exercises, and if you have the possibility to go further and try to deep on this, it will be quite helpful for you, because QGIS is very powerful for this type of supporting data analysis.
And okay, so maybe now one last one. Can QGIS be efficiently used? Again, I don't know if you have this experience, but on Apple Mac computers, I study climate parameters and mangrove health comparison. Can Copernicus data be used for this study? Okay, so two questions actually.
Question indeed for Apple. I tested also on Apple and QGIS.
Okay.
So even the plugin, I mean, the new version is very flexible and stable. And for the second, of course, if your research focus is on and assessing the health marine ecosystem by, let's say, studying with climate approaches, I mean, of course, the Copernicus marine data are a valuable source of information for that can support your studies, particularly, for instance, the reanalysis from the models or the long simulation that I was showing. I mean, I introduced that at the beginning, but as well also the huge catalog, available observational catalog that I guess yesterday it was quite, I mean, described widely by my other colleagues. So in this case, I would suggest to go through the Copernicus Marine Service product catalog and try to search which are the data that you need with the time period that is pertinent for your analysis, keeping also into account that we have recently also some new products that are the ocean monitor indicators that have been that are part of the marine Copernicus Marine Catalog and that can provide you some nice information from the climate point of view.
Thank you, Stefania, for your answers. And now we've reached the end of this session. We hope you have enjoyed today's practical session. We ask you just to take a few moments to answer our survey. This is very important for us to improve our coming workshops. So please take a few moments to just fill in Slido. You will have access to our survey and you will be able to answer it. I thank you all for your presence, to Alvaro and Stefania today. Thank you for your tutorials. They were very interesting, and this topic is definitely very, very important at the moment. We have been hearing more and more about marine heat waves. Thank you to all.
Well,
Thank you so much.